Welcome! Today we are diving deep into electrolysis, a really cool process that uses electricity to break chemicals apart. We're going to uncover the simple rules that control this whole reaction, so let's get right into it.
Here's our game plan. We'll start with the absolute basics, then we'll look at the simplest case possible. After that, we'll introduce a wild card, water, and finally, we'll crack the code that runs the whole show. Okay, first things first. We need to get to know the key players in this chemical puzzle. Let's do a quick fire round of the 4 essential terms you need to know to make sense of all this. So, what is electrolysis really? Well, you can think of it like a controlled demolition, but on a molecular level. We're basically using an electric current to very precisely split a compound back into its original elements. Now, the electrolyte, that's the substance we're actually zapping. And for this to work, its ions have to be free to move around, which means it needs to be a liquid, either melted down or dissolved in something like water. All right, now for the tools of the trade, the electrodes. First up, the anode. The easiest way to remember this is that opposites attract. The positive anode pulls in the negative ions, which we call anions, and when they get there, they lose electrons. That process is called oxidation. And its partner in crime is the cathode. Since it's the negative electrode, it attracts the positive ions, or cations. At the cathode, these ions gain electrons at a process we call reduction. So just lock this in. Anode is positive, cathode is negative. Simple as that. Okay, so let's see how all this works in the simplest possible scenario, a molten compound. When there are only 2 types of ions in the mix, one positive and one negative, predicting what's going to happen is, well, incredibly easy. Check out the pattern here. It's so clear, right? In molten sodium chloride, the positive sodium ion gets pulled to the negative cathode, and boom, you get sodium metal. The negative chloride ion heads over to the positive anode and forms chlorine gas. Same exact logic for lead bromide. It's just a clean 2-way split every single time. But things get way more interesting when we don't melt a substance, but dissolve it in water instead. And as you can see, this introduces a major plot twist to our story. So what is the big deal with water? Well, it doesn't just sit there and dissolve the salt. Oh no, it jumps right into the action and gets directly involved in the reaction itself. This slide just lays it all out perfectly. When the salt is molten, we get sodium metal, but add water and all of a sudden we're getting hydrogen gas at that same electrode. The anode product, chlorine gas, stays the same, but the reaction at the cathode is totally different. So why? Why does that happen? And here's the secret. Water isn't just a solvent. It actually breaks apart into its own ions, positive hydrogen ions and negative hydroxide ions. So now, instead of a simple 2-way choice, we have a crazy 4-way race on our hands. We've got 2 different positive ions racing to the cathode and 2 different negative ions racing to the anode. So if it's a race, there have to be rules that decide who wins, right? Well, in this section, we are going to become detectives and decode those rules so we can predict the winner every single time. This is the big puzzle we have to solve. With 4 different ions all competing, how in the world do we predict the products? It turns out it all comes down to 2 surprisingly simple rules. Okay, rule number 1 applies at the positive anode, and it's called the concentration rule. On the left, you see that in a concentrated solution, there are just so many chloride ions that they overwhelm the competition and win the race, producing chlorine gas. But on the right, in a dilute solution, the hydroxide ions from the water don't have as much competition, so they win, producing oxygen gas. So for the anode, it's all about concentration. Now for rule number 2, and this one is for the negative cathode. We'll call it the reactivity rule. Here, it's a head-to-head battle between the metal ion and the hydrogen ion. So if the metal, like zinc, is more reactive than hydrogen, it basically prefers to stay as an ion in the solution. It's happier that way, so hydrogen wins and you get hydrogen gas. But if the metal, like copper, is less reactive than hydrogen, it's much easier to turn it back into a solid metal. So the copper ions win and you get a nest coating of pure copper. And believe it or not, that's it. That's the whole game. With 1 rule for the anode and 1 rule for the cathode, we can now create a final formula to predict what's going to happen in pretty much any electrolysis reaction in water. And here it is, your official cheat sheet. Let's run through it. At the positive anode, if your solution is dilute, you get oxygen. If it's a concentrated solution with a halide, you get the halogen gas. Easy. At the negative cathode, if the metal is more reactive than hydrogen, you get hydrogen gas. And if the metal is less reactive, you get the metal itself. That's all you need to know.
So just remember, even though it can seem really complicated, by focusing on just those two things, concentration at the anode and reactivity at the cathode, you've officially cracked the code of aqueous electrolysis.
And this isn't just some abstract concept from a textbook. This process is happening on a massive industrial scale all around us. So now that you know the rules, just think about it for a second. What vital processes, from making the chemicals in our cleaning supplies to purifying the metals in our smartphones, do you think rely on this amazing power?